is something which worries me about DSM generation. I said before, in many, many tests we have achieved an accuracy of 1 to 5 pixels in DSM generation. Now these are 3 test areas in Switzerland where we have used prism stereo data, and we have run an image matcher and we have compared it with reference data, high accuracy. And these are the error distributions. They look beautiful. Gaussian distribution with a very high peak. Every data set includes a few million points, so a lot of points, statistically relevant, beautifully, all centered around 0. But what you don't see very clear is they also have long tails, which means large errors going up to 60 meter, pixel size 2.5 meter. And this is what worries us, okay? The system, or the algorithm, I should say, behaves well in most of the points, but there are always a few blunders and also systematic errors that are a reason to worry, and we have to get rid of those, okay? How we do it is a detailed technical problem that I cannot explain fully. Or another case with Cartosat data over the city of Rome, where we did the same. We had a reference DSM from area laser scanning, and we compared the result of the matcher finally with a reference DSM, and this is a color-coded picture of the residuals, of the errors. And you see clearly a systematic pattern, okay? You see the roads in Rome clearly showing up systematically, because what's happening is the roads are being filled or partially filled because of occlusion or semi-occlusions. So this is not really the result of matching errors. The points themselves may be correct, but interpolation errors. You don't get down to the foot point of a house, to the intersection of the wall with the road. So if you model the surface, you will generate an error. So many of these errors are really interpolation errors and not matching errors, but they are part of the digital terrain model. So this is something we have to grab. Now we can also produce city models, of course, from satellite images. Here's an example of Phoenix, Arizona. In this case, of course, the texture on the wall is generic, is synthetic. Now when we use aerial images, we have many choices, not only using cameras, but also laser scans, radar, INSAR, and so forth. A very interesting trend here is, of course, the use of multiple camera heads, like pictometry is using. Singapore, by the way, has also been flown with such a system, but for security reasons, we do not get access to this kind of imagery, unfortunately. We can use this aerial data to produce digital terrain models, digital surface models in a city. This is not the result of a laser scan, but it looks the same or similar. This is a result of an image matcher using Wechsel Ultracam over the city of Graz. And if you go into detail, you find out that the image matcher behaves better than the laser scanner along edges, okay? Houses are built up by edges. Why? Because the edges are directly matched. Laser scan, you will miss the edges, most probably. So you have to interpolate the edges. So generally, photogrammetry is better on edges, while laser scanning is better on soft surfaces. If I may simplify a little bit the problem, okay? Then we have semi-automated techniques to generate city models. And very useful is, of course, this oblique imagery. We have used in the past the vertical images to extract the geometry, and the oblique images mainly for texture. So this is, for instance, an example from London, city model of London, where we use pictometry images and we overlay the geometrical model with the oblique images, and there will be a difference, of course, because georeferencing original is not very accurate, and we do the corrections and we put the texture under the model. texture that comes from oblique images. Now you can use approaches for geometric approaches for very much detailed buildings, like they are used in car navigation, 3D landmarks for car navigation. I have something here on automated building extraction, but I go through it in the sake of time. And the main problem that automation fails comes from the fact that we have such a high variety, large variety of different buildings. There are some cases where modeling is relatively easy because we have repetitive objects, but other cases where it becomes very, very problematic. This is also a building which has to be modeled possibly. So this is the main problem where automated procedures are not intelligent enough and will fail. The main problem is really in image interpretation and automated control of level of detail, also to produce the correct topology. Look, if you look at this one, I don't know if you have done it in detail. This looks pretty good from your place. Huh? This is a 3D city model, but if you come close, like I do, then you see many, many problems. There are many houses which are in the middle of the road, so no correct topology. Okay? So how can a house be in the middle of the road? There's texture. The top of the building is being imaged twice, one times here, one times on the ground. There are houses which stand on cars, okay? So many, many problems, but it looks good from apart. It looks good from your place, but please don't go close. Huh? So this is the issue not only of geometry. The buildings themselves may be correct internally, but topology is totally wrong. And if you put it on a GIS, you cannot do any reasonable analysis anymore, because topology is wrong. Okay? So please pay attention also to topology. Another example, let me go through this one quickly. I've shown it on other occasions. We have now things like Google Building Maker, and people are talking about collaborative mapping, for instance, and they are producing things like this. Okay, look behind. I went to Google Earth and checked Taipei, and what I realized is you need a four-wheel drive in the city of Taipei. This is the DTM in Taipei. If you go to Google Earth, you know, in order to get up here with your car, you need a four-wheel drive, which I have in Switzerland, no problem. I'm prepared. Or here, this is Taipei. I know you know Taipei better than I do. I mean, we are far away here from the real situation. This is SIMT data, radar data, not good enough, of course. And this leads to the fact that some buildings are also swallowed. If you go to the Hyatt, some of us are in the Hyatt, you know, the lower part is chewed up by the digital terrain model. There's no entrance anymore. You know, and look at this feature, it's broken up. I mean, you can look around, you will find problems and problems all over the place. So this has been done, I suppose, by a non-professional, by collaborative mapping. Do we need collaborative mapping? Do we want it? I don't know. In Europe, you wouldn't find any customer, at least not in my environment. If I present this data to my architects, they kick me out of the department right away. Okay? So please be aware of the situation. Then we have street views. Street views are very popular among young people. You know, you have this car, which I saw in Thailand, the Google Street car, taking thousands and millions of images, and then processing the data fully automatically. I used Photosynth, the software, Microsoft software, on this data set in Singapore, Malay village, and it returned a point cloud, which is hard to understand. It is full of blunders. If you use a point cloud for modeling, you go nowhere, okay? Because you don't understand the structure. There are too many blunders, there are important points missing. So if you want to model this, you have to go back to the images and use image information for modeling. Point cloud is not good enough. This is what photosynth gives you, automatically, quick but dirty. Do we want this? I don't know. The same applies to other cases. This is a photogrammetric block, and this is what computer vision people are using. 2.8 days of processing unstructured data as opposed to 2.5 minutes. If you put a little bit structure into your data acquisition procedure. Unorganized, unstructured, as opposed to organized, structured. So problem of quality control pops up. What is accuracy and completeness? Completeness is also important for the customer. If you get a contract for city modeling and you have to model 100,000 houses and you miss one house, you will have a problem with the customer, of course. So please don't forget about completeness. And also, one of the problems from a scientific point of view, we have very little or no qualitative and quantitative studies about the different techniques in house modeling. You hear many, many papers if you go to conferences, but who is comparing these different approaches? So far, nobody, but I would hope in the future it will happen. Okay, I think I have to jump to the conclusion now. I wanted to say something about UAE as well, but for the sake of time, I will skip it, and I will go directly to the conclusions. Sorry for that. First of all, when it comes to automation, where do we stand? Fully automation. And here I always like to quote Rodney Brooks, who is called the Pope of Robotics from MIT. He's a very famous man in robotics. And he published an article in one of our books in our school, The Road to 2030, A Wide Ride. And I quote from him, and he's addressing navigation, but we can apply it to the generation of city models as well. The robots of tomorrow will need to have the object recognition capabilities of a 2-year-old child, which is a very pessimistic statement for us when we think about automation. The robots of tomorrow, so we are not yet there even, will need to have the object recognition capabilities of a 2-year-old child. This is where we are in terms of image interpretation. A big, big problem, and the final frontier for any remote sensing person and any photogrammetry person, anybody who works with images. And the question is always, is it a problem based on measurement or modeling errors? Can you understand this one? Can your computer understand it? Probably not. Huh? Even for you, it takes some time to understand it, right? Okay, so the conclusions is we have a lot of tools available, a lot of sensors, and also software available for documentation, analysis, and dissemination. Sensors, processing software, visualization software, spatial information technology, internet finally.